Hi, Miss Barber here. This lesson is titled The Definition of the Derivative. The three big ideas of calculus are the limit, the derivative, and the integral. The limit provides the foundation for both the derivative and the integral. Now that we have learned the basics of the limit, we will begin our study of the derivative. The secant line passes through 2 points, x, f of x, to x plus h, f of x plus h of a function, and gives the slope of the average rate of change by the formula, quantity f of x plus h minus f of x, all divided by h, provided that h does not equal 0. Although h cannot equal 0, we can let h approach 0 as a limit. In doing this, the 2 points used to form the secant line become so close together that they appear to be a single point, and the average rate of change over f over this interval becomes close to instantaneous rate of change. We will examine the transformation from an average rate of change between 2 points, a f of a and a plus h f of a plus h, to the instantaneous rate of change at a f of a to arrive at the formal definition of the derivative. The idea is to begin with the slope of the secant line between the x values a and a plus h and decrease the length of h. That is, to continually make h smaller, so in the progression we went from a downward slope to a horizontal, and then notice that the slope is now increasing as we continue to make the distance h closer and closer to 0 until it appears to occur at just that one point, a. We observe that as the h approaches 0, the secant line approaches the tangent line, and the average rate of change approaches the instantaneous rate of change. Definition: for y equals f of x, the instantaneous rate of change, or the slope of the tangent line, or the slope of the graph at x equals a, is the limit as h approaches 0 of, in the numerator, f of a plus h minus f of a, all divided by h in the denominator if the limit exists. Example 1.6.1. Graph f of x equals 2x plus 3, and the graph of the tangent line to f of x at the point 1, 5. The line itself is the tangent line, and at any point regardless, but let's go ahead and mark the point 1, 5, the slope is 2. Example 1.6.2. For the function f of x equals x squared minus 3x, a. Find the slope of the secant line from x equals 2 to x equals 3. To find the slope of the secant line, we find the average rate of change, and so we would find the function evaluated at 3 minus the function evaluated at 2 divided by 3 minus 2. These were the points given. Let's compute or evaluate the function at each of the x values. So at f of 3, we would have 3 for each x, so 3 squared minus 3 times 3, which turns out to be 9 minus 9, or 0. And for f of 2, we will have 2 squared minus 3 times 2, which would be 4 minus 6, which is negative 2. So let's replace. For f of 3, we evaluated that to be 0, minus f of 2, we evaluate it to be negative 2, divided by 3 minus 2 is just 1, and so 0 minus negative 2 is 2. We have evaluated the slope of the secant line from x equals 2 to x equals 3 to be 2. Part B. Find the slope of the tangent line at x equals 2. This means we need to be able to compute the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h. Let's compute the parts. F of 2 plus h will be the quantity 2 plus h squared minus 3 times 2 plus h. 2 plus h squared is 2 plus h times 2 plus h, which will be 4. Remember doing the FOIL. Then 2h plus 2h is plus 4h plus h squared, and then distribute the minus 3 to the term 2 plus h, so minus 6 minus 3h. Let's copy that, and then we'll combine like terms. 4 minus 6 is negative 2. 4h minus 3h would be plus h, and we still have h squared. We have previously computed h at 2, and that was, if you will recall, negative 2. Now let's put it all together. We want the limit as h approaches 0 of, and then f of 2 plus h is negative 2 plus h squared minus f of 2 is negative 2 divided by h. Let's simplify the numerator. So we'll have the limit as h approaches 0 of negative 2 plus h squared minus negative 2. The constants cancel, and we are left with h plus h squared in the numerator divided by h. We can factor out a common h in the numerator, which will give us the limit as h goes to 0 of h times 1 plus h divided by h, and the singular h in the numerator and the 1 in the denominator cancel, and now we can take the limit as h approaches 0 of 1 plus h. When h goes to 0, the value we get is 1. The slope of the tangent line at x equals 2 is 1. And now the formal definition of the derivative. Definition: for a function y equals f of x, its derivative at x is the function denoted f prime and is defined by the limit as h approaches 0 of, in the numerator, f of x plus h minus f of x, all divided by h in the denominator, provided that the limit exists. If f prime of x exists, then we say that f is differentiable at x. The derivative of the function f is a new function, f prime of x. The derivative can be used to give the instantaneous rate of change of f at x for each x in the domain of f prime of x. Next example, find f prime of x by the definition of the derivative for the function f of x equals 7x plus 4. Let's begin by writing the definition of the derivative. That is, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Let's find the components. For f of x plus h, we will replace every x in the function with x plus h. So we will have 7. Then for the x, x plus h minus 4. And simplified, that'll give us 7x plus 7h plus 4. Now let's compose. We will have the limit as h approaches 0 of, and for f of x plus h, we will replace that with 7x plus 7h plus 4. And then we just subtract the function. That's what f of x is. So we will put in 7x plus 4 for the f of x divided by h. Let's distribute the negative and continue to simplify. So we will have the limit as h approaches 0 of 7x plus 7h plus 4, then minus 7x minus 4. We are distributing the negative, divided by h. The 7x's and the 4's cancel. So in the numerator, we'll write first the limit as h approaches 0 of the term or terms remaining in the numerator are just 7h. And then in the denominator, we have h. The h in the numerator and the denominator cancel, and so we end up with finding the limit as h approaches 0 of 7, which is just 7. And it matches with the idea that for the lines f of x equals 7x plus 4, the slope is 7. When we use the definition of the derivative, we also get 7. Example, find g prime of x by the definition of the derivative for the function g of x equals negative 5x squared, and then find the derivative at 1 and the derivative at 3. Let's begin with the definition of the derivative, which states g prime of x is equal to the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. Let's find the components. So for g of x plus h, in the function we will replace with x plus h every place there is an x. So we will write negative 5 times x plus h quantity squared. Algebraically, that's negative 5. And then x plus h times x plus h twice, which will give us negative 5 times, and then multiplying using FOIL, x times x is x squared. The inside is xh, the product of the outside is xh, so together you have 2 xh's, and then the product of the last terms would be h squared. Now distribute the negative 5, so you have negative 5 x squared minus 10 times xh minus 5 times h squared. Let's put it all together. So now we will have the limit as h approaches 0 of, and for g of x plus h, we will replace that with the expression negative 5 x squared minus 10 xh minus 5h squared, and then subtract g of x, which is negative 5x squared, all of that divided by h. So this will be equal to the limit as h approaches 0 of, and in the numerator, the minus 5x squareds cancel, so the remaining terms will be negative 10 xh minus 5h squared divided by h. Let's factor out an h from the numerator, so we will still have the limit as h approaches 0 of, factoring out the h, negative 10x minus 5h divided by h, and continuing. We will now have the limit as h approaches 0. The h in the numerator and the denominator cancel, so the limit as h goes to 0 of negative 10x minus 5h, and taking the limit as h goes to 0, the remaining will be negative 10x. So we get to conclude that by the definition of the derivative, g prime of x is equal to negative 10x. We have got the derivative function. Now let's evaluate at the specific values. To compute the derivative at 1, we evaluate the derivative function negative 10x by putting in a 1 every place there is an x, and the result is negative 10. The derivative at 3, that's the instantaneous rate of change of g of x equals negative 5x squared at x equals 3 would be negative 10. Putting in 3 for the x, that'll give us negative 30. Derivatives are often used to find 1. The slope of the tangent line to a function at a point on the function, and 2. The instantaneous rate of change of a function at a point on the function. Example, use the fact that for g of x equals negative 5x squared, the derivative g prime of x equals negative 10x to find the equation of the tangent line to y equals g of x at x equals 3. We need 3 pieces of information to get the equation of a line. They are: we need the slope of the line, we need a point on the line, and we need to be able to assemble an equation for the line. So let's begin with the slope. The slope is the instantaneous rate of change, and we are given that the derivative function is negative 10x. We need the slope at x equals 3, so we compute the derivative at x equals 3, which would be negative 10 times 3, or negative 30. The slope is negative 30. It is decreasing rapidly. The point is an ordered pair. You need an x, comma y. We are given that the x is 3. We need a corresponding y value, which you get by evaluating the x in the original function. So now we have that the g of x is equal to negative 5x squared. To compute the corresponding y value, we evaluate the original function at 3, so you're going to have negative 5 times the quantity 3 squared, which is negative 5 times 9, or negative 45. The ordered pair is negative 45. Now, in order to get the equation of a line, we typically use the point-slope form of the equation of a line, so we will use y minus y1 equals m times the quantity x minus x1, and then we will solve. So we'll write this as y minus the corresponding y value that we just computed for the point is negative 45. The slope is negative 30. And then x minus, we were given the actual x of 1 point, which is 3. So we can write this as y plus 45 equals, distributing negative 30x, negative and negative gives us a positive 90. Solving for y, you get minus 30x. Subtract 45 from both sides. 90 minus 45 will give us a positive 45, and now we have the equation of the tangent line. Example, use the fact that for the function g of x equals negative 5x squared, that the derivative g prime of x equals negative 10x to determine where the tangent line to y equals g of x is horizontal. In order for a line to be horizontal, the slope must be 0. Therefore, what we are solving here are for the x values, if any, where the derivative equals 0. Horizontal means that the slope is 0. Therefore, we will solve the function. The derivative g prime of x equals negative 10x for it to equal 0. 0 is equal to negative 10x. Solving for x, we get that x equals 0. So we conclude that g of x has a horizontal tangent line, at x equals 0. Example, for f of x equals 6 divided by x, find the derivative f prime of x. Please see completed example in the student notes. Differentiability. A function f of x is not differentiable at a point if 1. The function is not defined at the point, 2. If the function is discontinuous at that point, or 3. The function has a corner or a kink at that point. Example, determine where the graph is not differentiable. Let's observe by beginning from the left side. We see that at x equals negative 6, we have a solid dot, but nothing to the left of negative 6. So at x equals negative 6, the derivative does not exist or is not differentiable because the limit as h goes to 0 does not exist at that point. The next point at which the graph is not differentiable is at x equals negative 4. We have a kink or corner at that point. At x equals negative 2, the graph has a discontinuity. Therefore, the graph is not differentiable. Again, at x equals 0, the graph has a discontinuity. Therefore, the graph is not differentiable at that point. At x equals 2, we have another corner or a kink. Therefore, the graph is not differentiable at x equals 2. And finally, at x equals 4, we have an infinite discontinuity. Therefore, the graph is not differentiable at that point.